Hello everyone, I am Ziyang, a current PhD student from the University of Pennsylvania. Welcome to my talk on our paper, ARBITRAR User-Guided API Misuse Detection. Software APIs exhibit rich diversity and complexity, which not only renders them a common source of programming errors, but also hinders program analysis tools for checking them. According to a recent study, 17% of bugs stem from API misuses. These misuses can, of course, have serious security impact. Let's look at one example API, Open, and you will see how such a commonly used API poses great challenge to an API misuse detector. So Open returns an integer file descriptor. On success, the return value is non-negative. Otherwise, the user must handle the error. When the call succeeded, subsequent read might be called, and the file descriptor must be closed at the end. The above example shows the correct usage as it contains all of the above. But this example shows a misuse as the file descriptor is not being checked and therefore error won't be handled. In this case, the user does some check on FD, but the check itself is incorrect. According to the specification, the FD on success will be non-negative but not non-null. And this is again an API misuse. This time we show another check of FD which compares to 0 with predicate greater than or equal to. Although different than the first example, this one is actually a correct check as this if-then branch is a success branch. The real problem with this code snippet is that the file descriptor is not being closed, hence another misuse. What could further complicate this API is this last example. Now the result of Open is being stored into a config struct. After a correct error handling, the config struct is being returned, and the ownership of FD is being passed to a parent context. Although there's no call to function close, this could pretty much be a correct usage as we can expect the caller to close this file descriptor. I hope you see that there are many ways which the API usage could be correct or incorrect, and sometimes even in between. They all contain subtle details that differentiate one from another. Next, let's look at a less commonly used function, PNG destroy write struct. This function is a deal allocator function provided in libpng. People usually use this API in the following way. First, the user creates a PNG struct using PNG create write struct. And then, by passing in the PNG pointer, people call PNG create info struct to create an info pointer. At the end, people free both the PNG pointer and the info pointer simultaneously using the PNG destroy write struct. Also, it is okay for the user to pass in null for the second argument. In that case, nothing will be done to the info struct. In this code snippet, there are two calls to PNG destroy write struct. The first one happens when the call to PNG create info struct fails. In this case, we don't have a valid info pointer, therefore we pass in null as a second argument. On line 8, on the other hand, we can assume both PNG pointer and info pointer are valid. Therefore, we should pass in info pointer as the second argument. But unfortunately, it fails to do so, which results in info pointer not being freed, hence a memory leak. Notice that the second usage is called with exactly the same arguments as the first one, yet it's still an API misuse. This suggests that the analysis of API misuse have to have very detailed information about the calling context. Let's then talk about the existing tools on finding those API misuses. We can roughly divide them into two categories. Category A assumes API usage follows simple idioms that can be mined from the code. For example, API send will scan multiple code bases and collect all of the usages of one particular API function. Given a predefined pattern, it will find among those usages the majority and the minority. If there is statistically significant minority, these minorities will be reported as alarms. These tools are very easy to use. The user don't need to know anything about the tool nor about the API since the specifications are mined for code. Therefore, the users are usually just one command away from the bug report. But the problem now is that they assume we have large corpus of code and a clear majority and minority. This does not usually hold simply because of a complexity of the real-life APIs we just showed earlier. If this is applied to that PNG destroy write struct function we mentioned earlier, API send won't work because there's no huge corpus of code to mine in the first place. Also, it relies on predefined patterns to perform statistical reasoning, which could make it hard to generalize to arbitrary API specifications. On the other hand of the spectrum, we have tools that give the end user full control, that is, writing the API specifications. Examples of those include SAML, Sys, and IAM-Checker. Usually these tools provide domain-specific language for the user to write specifications. These tools are very powerful as the user can write quite complex specifications, but the problem is also quite obvious as writing the specification requires expertise and time. Meanwhile, if an API is less commonly used, people might not find it worth it to invest time writing specifications. That also implies that the effectiveness of these tools depend on the quality of the specifications written by the human. Meanwhile, although having lots of differences, these tools from both categories are used in the same following way. The mine idioms or user-written specifications are passed to an API misuse checker, and the checker then produces a bug report. The user needs to investigate the whole bug report and see if any of the alarms are real bugs. If the false positive rates are very high, this investigation process is very frustrating for the end user. So now we raise the question, can we enable regular programmers to find API misuse for arbitrary APIs? We list our 3 key ideas. The first one being that looking at a usage, regular developers can easily determine its validity. The key idea 2 is that we can actually leverage users' investigation of those bug reports and learn from the user feedback by using machine learning models. The final key idea is that we can use active learning to actively propose new API usages, allowing the users to find bugs even faster. So we propose our solution, user-guided API misuse detection. Our solution, ARBITRAR, is an interactive tool for finding API misuse bugs. It operates in a 2-phase mode. The first one being analysis, and that phase produces API usage databases containing a lot of program traces around the API. And secondly, we enter a user interaction phase that allows users to participate and find API misuse bugs. With this design, we have the following 4 goals. The first one is efficient trace generation. Our ARBITRAR should work on large projects such as Linux kernel. Secondly, it should have generic trace representation. This is to deal with arbitrary API with diverse specs, and this representation should enable the machine learning model to learn API usages from scratch. And third, we should have real-time user interaction, because interacting with the user should be quick and responsive so that user doesn't get frustrated when finding the bugs. Last but not least, we should have very accurate alarm identification. We should accurately identify buggy API usages so that the user can confirm an API misuse within just a few rounds of interaction. And the last point is actually the most important one among these 4. So how do we do it? The first phase is ARBITRAR's analyzer. It basically performs under constraint symbolic execution to produce a database containing symbolic traces. We only need source code and a target API name to collect all of the symbolic traces around this target API. The symbolic traces are then passed into feature extractor to produce Boolean features. The feature extractor analyzes the traces and extracts information regarding a function call and its context. For example, return.checked is a feature telling whether the return value of the target function call is being used in a branch condition. Another example, invoked before lock being true suggests that a lock function is being called before our target API call. While this set of features is able to cover most of the known API specifications, this is easily extensible. The Boolean features are then passed into a binary encoding and gets turned into a fixed dimensional vector containing only 0 and 1s. Now this representation is relaxed from the logical domain into numerical domain and could be easily used by machine learning algorithms. In our final step, we feed the encoded traces into our active learning algorithm and start the interactive process with the user. At each iteration, our active learning algorithm picks a trace with API usage presented to the user and asks for user feedback. The user will see pure code showing the trace and provide simple bug or non-bug feedback, basically just yes or no feedbacks. The learning algorithm will learn from the user feedback and propose the next trace, and thus staying inside the loop. Recall that our goal here is to propose buggy API usages as quickly as possible. So how does the active learning algorithm pick a trace to achieve that? Let's first assume P the set of positive traces labeled by the user, and the set of negative traces, and U the set of unlabeled traces. Initially, all of the traces are unlabeled, so U will be the full input dataset and P and N will be empty sets. As the user provides more and more feedback, the sets P and N will be gradually populated. To select the most likely bug, we do a very simple thing. That is, select the unlabeled trace that is the closest to the bugs and furthest from the non-bugs. This is simply reflected in the formula below. The function g here is a scoring function that gives each unlabeled trace a score based on the known positive traces and negative traces. For each reiteration, we simply select the x from u that has the maximum score g. Note that the difference between closest and furthest estimates the maximum discrepancy, which we call MD, while the k function inside the formula is the kernel density estimation, which is KDE. Hence, we get our algorithm name MD-KDE. This table shows an actual run-through of our active learning algorithm. In this example, we want to find API misuses with the function png_destroy_read_struct. In the first iteration, our algorithm randomly picked a trace marked in the blue triangle, and the user labeled it non-bug, suggested by the green cross on the second plot. Immediately in the second iteration, our algorithm encountered an actual bug by picking the one that is the furthest from the first non-bug. That is indicated by this red plus sign in the third graph. In the third iteration, our algorithm picks the one that is the closest to the previous bug, getting us the second bug. And this process goes on until user suggests stop. Finally, we come to our evaluations. This table shows that within just 5 rounds of iterations per API method, we are able to find 89% of the bugs listed in our bug benchmark dataset, which outperforms API send with a wide margin. This chart shows that the percentage of bug detected with respect to the number of iteration. So what you can see is with 0 iteration, the user is not able to find any of the bugs, but as we interact with the system more and more, let's say at iteration number 5, we are able to find 89% of the bugs. And with at most 20 iterations, our tool finds all of the bugs listed in our bug benchmark presented by API Send and API MU for C. Then we applied our tool to Linux kernel 5.7, OpenSSL, libpng, libbluetooth, and many of their dependent packages. We found 40 bugs in total, and on average, we find the first bug with only 3 rounds of interactions per API method. Lastly, we show that our active learning algorithm is running at real time. Due to the design of our MD-KDE algorithm, we are able to optimize it to use rank 1 update, which executes in linear time complexity in each iteration. This enables the user to get real-time feedback and reduces users' wait time, as we see in many other static analysis tools. In conclusion, we present ARBITRAR, a user-guided API misuse detection tool. Secondly, we propose MD-KDE, a novel active learning algorithm that is fast, precise, and well-fitted under API misuse detection setting. Last but not least, we perform an extensive evaluation of ARBITRAR. Our tool not only outperforms existing tools, but also finds 40 new bugs in 3 rounds of user interactions on average per API method. The source code of our tool ARBITRAR is publicly available at the following URL. Thank you.